And let's do a physics question. So the first one is just no points involved, just a survey question. But this one is an actual question, and I'm going to try to do it as a demo. We'll try to swing this around counterclockwise, and I'll try to release it right when the string, I'm not going to break the string, but if I release it right when the string is horizontal, which way do you think it'll go? Let's try it. Oh, that wasn't very good. Let's try it one more time here. I think I released it a little early. It's a little hard to do this. Yeah, it's a little bit better. Anyway, see. So, idea being that when an object is in a circular path, let's just look at this. It has a velocity at any moment which is tangent to the circular path. And there is a force also on it giving it a inward radial acceleration, sometimes called centripetal acceleration, exact same thing, which keeps it on the circular path. But if that force is taken away, then it'll go on at a constant velocity in a straight line with whatever its velocity was when the force went away, which is that tangent. Okay? Believe it or not. So, there's a lot going on in this slide, but this is the phases of the moon, and I remember actually really clearly, I took astronomy in my first year here at University of Toronto, and on the first term test, one of the questions was, what is the phase of the moon today? And I remember after the class, everyone was freaking out, what an unfair question it was and things, and I just kind of kept my mouth shut because I happened to know I was happy because I remember last weekend watching the full moon, for example. I think it was just about full moon, probably on Saturday night. I was at a party, and so now I think it must be like waning gibbous or something. But anyway, if you look up at the sky a lot, you just kind of get used to it. Every month the moon goes around, and because of the relative orientation of the sun and the earth and the moon, you see there's always half of the moon is always illuminated by the sun and half of the moon is not, and it is in darkness. But depending on our perspective of it from here on the earth, if it's over here, we see that lit half, and so it looks full. If it's over here, we don't see it. It's like the new moon. In between, when you just see it after a new moon, that's when you sort of see it just after the sun sets. And so we're right around here, so I'm sort of waning gibbous. Just before the new moon, you'll see it just before the sun rises. Okay. So, it's just after the sun sets. Okay. So here's Isaac Newton, long, long ago, wondering why the moon goes in this circular path around the Earth. If you have the ball and the string, you have the string, right? The string is pulling inward towards the center. So he was looking at the moon and thinking, there's got to be some sort of inward force pulling the moon towards the Earth. And then the apple fell on his head, and he put the two and two together and was correct. So the idea being that any two massive objects are attracted to one another by a force. The force has got an equation for it. It's gm1 times m2 over r squared, where I think the g there is 6.67 times 10 to the minus 11 newtons times meter squared per kilogram squared. That's the universal gravitational constant. So this is the discovery of the universal gravity. And you can measure it. So what I'm actually postulating is that between any two masses, me and, I don't know, that speaker over there, we're attracted to each other a little bit because we both have mass. or any two people in this room are attracted to each other because there's mass and that's pulling you towards each other. And you can, this is a picture of the Cavendish experiment, which you can do in Physics 224, practical physics. There's two lead balls, two big lead balls, and there's two smaller lead balls inside the thing, and they're hanging on a little pendulum on a torsion wire, and they oscillate back and forth, and depending on your orientation of the big lead balls around, they settle to a different equilibrium location because of the gravitational attraction between the balls of lead. So you're measuring there 10 to the minus 8 newtons. So 10 nanonewtons is around the size of that force. Very, very small, but it takes around 2 weeks to do it. You can do it. You have to, if someone like opens the door while you're doing it, then it throws off your laser beam and you yell at them and stuff like that because you need the air currents to be very low in the room. But okay, so let's do an example. If there's two objects, we're going to call them object O. This is a Sharpie. Don't write on the screen with a Sharpie. Sounds like there's a joke there. Okay. Two objects, object O and object E. I don't know why I've called them that, but let's just call them that. Object O is at the surface of object E. Object E is this giant spherical rock floating in space, which has a mass of 10 to the 24 kilograms and a radius of 6,400 kilometers. First of all, what is the force of gravity of E on O? And the question B will be, can you think of a good name for object E? And there's a bonus point if it starts with the letter E, I guess. Okay. So the distance here, we're going to use this equation that F is equal to capital G MO ME divided by R squared. And R is this distance between the centers of the two objects. So R equals 6,400 kilometers equals the distance, that's important, between the centers. Center of mass of the two objects, And I haven't really done this very well. This is MO and this is ME, sorry. Do that in black to fix my slide there. Okay, so we've got a system. I guess the system here is just MO, and the force of gravity, F of E on O, is to the left, pulling it towards the center. It's because it's an attractive force. So F E on O is equal to 6.67 times 10 to the minus 11 times MO times 6 times 10 to the 24 divided by, I guess R is equal to 6,400 times 10 to the 3 meters, because there's 10 to the 3 meters in a kilometer. So let's just put that down here. 6,400 times 10 to the 3. I have to type that in my calculator and then square it. And when I type all these numbers into my calculator, I actually get 9.8 times MO. So does that number look familiar to you? Does anybody have a good name for this? Large rock, yes? Earth, yeah, okay. I like that name. Okay. I don't know. Units are, it's important to keep it units, newtons per kilogram, aka same thing as meters per second squared. So that's where this whole equation comes from. We have gravity for earthlings. So the real equation is in the upper left there. It's the G, capital G times M of something times M of another thing divided by some distance squared. But if you happen to be living on a large planet of radius 6,400 kilometers and a mass 6 times 10 to the 24 kilograms, you can write that equation more simply as, this is a short form, okay, where G is capital G, lowercase g is capital G times the mass of the Earth divided by the radius of the Earth squared. That's where that number comes from. Turns out to be about 9.8. And it actually changes with R, right? If you go up a mountain, then your distance from the center of the Earth is a little more. So gravity goes down to around, you know, well, actually up in an airplane or something like that, it's as low as 9.71. If down at sea level, it's 9.83. Here in Toronto, it's around 9.80. So that's what we use usually in this class. Okay. So that's good to know. And then there's this idea that it pulls towards the center of, so the direction, this is just the magnitude, but the direction is toward the center of the Earth. This is the part that's a little hard to believe, because it would mean that people standing on the opposite side of the Earth are upside down, and all of their stuff is upside down as well. And that's exactly what we think, right? So, okay, this sort of causes time zones and things, because the sun will be in different directions depending on what your direction of gravity is. If the sun is sort of in the opposite direction of gravity, we call that lunchtime, right? If it's the same direction as gravity, we call that midnight, right? So depending on where you are, what the direction of gravity is, that gives you your time zone on Earth. So time zones, to me, sort of prove the curvature of the Earth. And the curvature of the Earth has some interesting properties. So first of all, it turns out that if you go sideways about 8 kilometers, then the Earth curves downward about 5 meters. And if you use d is equal, you drop something from rest, d equals 1/2 at squared, then it's, if it's g, so falling is something like d is equal to around, well, 4.9 times t squared. In 1 second, object with 0 vertical speed, vertical initial speed, falls 5 meters. So what I'm trying to say here is that if you were to launch a ball horizontally, there it is, the initial y component of the velocity is 0. Do you remember when we did that experiment where we dropped something and also shot it off horizontally, and it kind of fell at that same rate? Because the y component and the x component of the motion are separate. So the x motion has 0 acceleration, but the y component has this negative 9.8 meters per second squared. So what I'm saying is that it falls 5 meters in 1 second. If your horizontal speed is 8,000 meters per second, then the ground will drop off 5 meters as your object falls 5 meters. So the ground is the same distance as it was a second ago. So try to consider what that's going to look like. If your horizontal velocity component is 8,000 meters per second, then you are no closer to the ground because of the curvature of the Earth. It'll actually seem like you haven't fallen at all. You'll still be 5 meters, well, I guess you'll now be 5, I guess you'll still be whatever distance you were originally. You will fall 5 meters, but the Earth will curve away 5 meters, and so that distance will be the same. If you were like 1 meter above, you'll still be 1 meter above. So, and this is this idea of orbits. So here we are, here's a little cannon. If it gets fired out some distance, it falls down and hits the Earth. If you go faster and faster, different speeds, so this is like v initial keeps on getting greater. As v initial gets bigger and bigger, there is this path c where for every 8,000 meters you go to the right, the ground drops off 5 meters, and you just stay the same distance. And so if you throw the ball that fast, then eventually it hits you in the back of the head 90 minutes later, as it turns out. So this is getting into this idea of that's how things orbit. There's sort of a new space station that's just recently, this is an artist's conception of what it will look like, Tiangong Space Station, operated by China. The main core component of it, which I think might be this part, was launched last year, and there's actually 3 people up there right now working on it. There they are, Chen Dong, Kai Shuji, and Liu Yang. So that's one. There's an international space station, which has been up there since 1998, I think, also in low Earth orbit. That's run by NASA and also Russia. Russia is now threatening to kind of pull out of the whole project because of all the mess over there in Ukraine. But they're up there right now doing environmental research, or I guess microgravity research. But what I want you to focus on is some of these orbital parameters. So if something's going in a circular path at this 7.66 kilometers per second, you should be able to figure out the radial acceleration, where the radius is going to be whatever the Earth's radius is plus this altitude. Altitude is how many kilometers you are above sea level, right? So I think if you just add it, you get 420 kilometers plus the radius of the Earth, which is 6,370, a little bit more accurately. You get 6,790 kilometers is r, the radius of the circular path. So equation 5.3 for acceleration would be 7.66 kilometers, so 10 times 10 to the 3 meters per second. We have to square that and divide it by 6,790. Again, I like to convert things to SI units, just meters. And we'll get, I think we end up with meters per second squared. I got 8.6 meters per second squared. Interesting. And which way is that? This is toward the center. It's centripetal acceleration of the circular path. So I have some questions. And there's people up there in the International Space Station right now. Here's one of them, Jessica Watkins. Let's go to this question right here. Jessica Watkins, there's her Instagram, is currently on the International Space Station, which orbits 420 kilometers above the surface of the Earth. This is called low Earth orbit, where a lot of things that we launch are sitting. Assuming Jessica has not changed her mass since moving to space, what is the force of gravity of Earth on Jessica? Is it 0, A0, B, the same as the force of gravity on her was when she was on Earth? C, a little bit less than the force of gravity on her while she was on Earth? Or D, not exactly 0, but much, much less than the force of gravity on her while she was on Earth? Let's give you a minute to think about that. Think pair share with your neighbor. Okay. Going once, going twice. Ooh, this is controversial. Again, I kind of wish I didn't have the green error bar, but I do. okay, or histogram bar. But this reveals what I think. Yeah, so this is related to that 8.6. It's not 9.8. It's less, but it's certainly it's a low Earth orbit, right? So let's go to another question. Okay, here's another way of looking at it. You are now some distance from the center of the Earth. And if you were to use the equation, the real equation for gravity, g m1 times m2 divided by r squared, then the r you use is the distance between the center of you and the center of the Earth. So we have to do that same calculation now for Jessica Watkins between the center of her and the center of the Earth. So what's the ratio there? How much farther is she from the center of the Earth than you are right now? She's up there doing some experiments in microgravity, like immunology experiments, actually. She's just a biology researcher. Let me spell it out for you guys here. Okay. This one's going a little better. Going once. Going twice. Survey says, oh, people are still clicking in. Let me give you another 5 seconds. And stop. So when it's phrased like that, the answer is 1.07, which is correct. So basically what I'm saying here is that low Earth orbit's really not that far up, actually. So Jessica is 6370 plus 420 equals 6790, and 6790 kilometers divided by 6370 kilometers is about 1.07. That's where that's coming from. So, okay, here's another question. Let's keep going through these. I actually found that this radial acceleration or whatever is 8.6 meters per second squared. So and also, if it's influenced by gravity, but just a little less gravity, then you would say that Jessica and the whole crew of the International Space Station is accelerating towards the center of the Earth at 8.6 meters per second squared. So why doesn't it crash? So read through these 4 answers. I think 3 of them are dead wrong, and 1 of them is correct. Please maybe choose your favorite and explain it to your neighbor. I'll give you, again, let's do a minute or so. guys got an answer? Let's go take a look. Going once, going twice. Ooh, yeah, this is looking pretty good. So I think you guys are in synergy with me here. We got it. So it's going sideways. That's the whole point, right? It would go off at a constant velocity in a straight line if not for this acceleration, which keeps it in a circular path. That's the point. So, okay. So the one I like there is this sideways acceleration. It certainly is true. The 8.6 meters per second squared is true. There's no rockets blasting it. Things that go up into orbit just stay in their orbit forever. Okay? It's because they have velocity, so their own inertia just carries them around. And yeah, it would crash pretty quickly if it was dropping at 8.6. If you took away the velocity, it would hit the ground in not very much time. So this is, I guess, from her actual Instagram account a few days ago. Just another day in the life on ISS. So she's doing a microscopy on the ceiling, which is interesting. This is her lab. She's put stuff on all the walls. There's no gravity, so she can just float around and just go to whatever experiment she wants to do. Instead of putting things on tables, we put it on the walls. And I think, I don't know what this is exactly, but it's something to do with looking at human immune function in a microgravity environment. So anyway, she's floating around, definitely. So why is that? Well, I thought it was this 8.6. So I think what's happening is that the whole thing, including Jessica, is accelerating towards the center of the Earth with this 8.6 meters per second squared, a little less than 9.8 because of this extra 1.07 distance. But it's kind of like if you were in an elevator and the elevator was accelerating downwards at 9.8 meters per second squared, you'd be floating around too. Because there'd be no normal force on you, right? The only force on you is gravity. You're a projectile. And until the elevator stops. But when you're in the space station, you're accelerating downwards with this, now it's 8.6 meters per second squared. You're going by down, I mean towards the center of the Earth. And since the whole space station's always accelerating, you feel weightless for the exact same reason that you would feel weightless if you were in an elevator going down. Not because there's no gravity on you. You haven't gone that far from the Earth. You're only just in low Earth orbit. But it's because you're accelerating. The whole spaceship's accelerating downwards. So let's go through this another way of looking at it. This is my big question. How fast do I have to drive my car to feel weightless? So what we could do is draw the car on the Earth. Can you imagine this? This is like Earth. And here's my car. This is not to scale. But I've always wanted to know this. If I drive my car this way at some v at speed, at what point will the wheels stop touching the ground because like I'm in orbit? So oh yeah, so what I'm going to do first is I'm going to neglect air resistance. That's always good to do. And all resistance. Sort of like haha. But the circular path is that I'm going around the Earth, is the surface of the Earth. Yeah, we're good. And then so this distance from here to here is r. R is equal to 6,400, roughly, times 10 to the 3 meters. Okay. And so the force diagram, of car looks like this. mg. So assume no normal force. So no normal force, remember normal force is self-adjusting. So if I guess I drive my car fast enough, I'm postulating that the wheels just lift off the ground a little bit and the car kind of just flying along. Can we imagine that? So A sub r is equal to v squared over r. Define plus r to be downwards, I guess, so that the sum of all forces in the f direction, in the r direction, the sum of all directions in this downward r direction is equal to the m times ar, so it's just mg, the only force, is equal to mv squared over r. The m's cancel, so it doesn't matter how massive your car is, there's going to be a particular speed. And it is v squared equals g times r, so v is equal to the square root of g times r. And you can plug those in, 9.8 times 6,400 times 10 to the 3. And this one's in meters per second squared, and this one's in meters. So it's meters squared per second squared. Take the square root, and I get 7,900 meters per second. Oh, there's that 8,000 meters per second again. Falling 5 meters for every 8,000. So anyway, that's the speed that you would have to drive your car. 8 kilometers per second. So that's kind of fast, I guess. There's 3,600 seconds in an hour, right? So I guess that's 3,600 seconds times 8 kilometers. So it's about 29,000 kilometers per hour. Faster than my car can go. But if I could drive that fast, maybe in a really fast car or maybe a motorcycle, then I'd be in orbit. So here's another learning catalytics question. I don't know what you guys think about this. This all seems maybe a little pie in the sky. But let's think about this low Earth orbit. There's Hubble Space Telescopes in low Earth orbit, International Space Station, this new Tiangong, they're all in low Earth orbit. And they all seem to have altitudes that's above 300 kilometers, but less than around 500 something. But why can't they have a orbit that's less than 300 kilometers above the Earth's surface? Anyway, again, 4 of these reasons are not correct, and one of them is the real answer. So if you see it, if you spot it, tell your neighbor. Hey. Remember, it's 0.8 points for answering anything, and an extra 0.2 for getting it correct. So I really like only one of these answers. Let me give you another 10 seconds. See if you can get it. Oh dear. Well, going once, going twice. This didn't go so well here. What's the answer? It's all about the air resistance, folks. It's the air, okay? That's the whole problem. I can't drive my car at 29,000 kilometers per hour because the whole thing would immediately vaporize. it would burn up, including me, because of air resistance. Air resistance generates heat, and if something's driving at 29,000 kilometers per hour, I'm here to tell you it will immediately explode in a giant fireball and be gone. Plasma, vaporized within less than a second. You wouldn't even find my bones, okay? So, and that is exactly what happens when a satellite, for example, that's orbiting the Earth does get too low. As it gets too low, it burns up and becomes this meteor and streaks across the sky, and people go, oh, look at the pretty light. And it's on their dash cam or something like that, and you see all these great videos of things, little rocks or something like that, that enter the Earth's atmosphere at this speed, usually around 8 kilometers per second. Boom. And all these other answers are just not the correct answer. Certainly, the gravitational pull is just about the same in low Earth orbit as it is down here on the ground. So that's just not at all correct. It's the speed which is keeping you in orbit, not the lack of gravity, right? And I don't know about this too far from the sun. The distance is very small. If you compare the distance to the sun, which is millions of kilometers, yeah, C is it. Too much air resistance, and it would fall or burn up. Lower than that, yeah, the radio interference. Again, radio waves travel right across the whole universe, so it's not going to make much difference if you're 300 kilometers up or not. And you can't communicate with the whole Earth at one time in low Earth orbit. You have to go much further than that to even reach half the Earth's. So that's it. Basic idea, you position a satellite up above the Earth's atmosphere. It's only about maybe 10 or 100 kilometers before you get to almost a pure vacuum up there. You're above air drag. There is a little bit of, you're getting into kind of the interplanetary medium when you're up there, and so there is some drag, and so you actually will have periodic booster rockets which try to compensate for that. But you don't often need to turn those on. Okay. So good. And if you got that extra 0.2 points, that's extra good. Okay. Well, what time is it? I got about 12 minutes. I just wanted to tell you, it's just sort of like astronomy now, but it is important, and it is in your book. So let's go through a little bit. These are some sketches that Galileo drew in 1609. So around this time, there were telescope manufacturers. A lot of the Dutch were the first ones to really make the great telescopes, and these were mostly used at sea to see other ships far away and try to figure out, you know, how many cannons they had or something like that. But Galileo was the first person to take one of those telescopes and look up with it at the heavens. And first of all, he got obsessed with the moon and was drawing lots and lots of pictures of the moon, which you can sort of see there. You can see all the craters on the moon. That's always fun to look at. And then he saw other interesting things, which was, what was known back then was that there were 5 particular stars that, unlike most stars in the sky, which are always in the same constellations, there were 5 wandering stars called Mercury, Venus, Mars, Jupiter, and Saturn. So they look like stars, but they don't stay in their constellations. They kind of move around in the sky and against the background of constellations. And when Galileo looked at those particular planets, as they're called, they no longer look, when he looked at stars, they looked like little teeny points. You couldn't see anything interesting. When he looked at the planets, they looked like disks, and he could see them in the telescope resolved. And you know, so there was even phases of Venus, which was sort of interesting. These are his pictures of Venus, where it would get bigger when it was in these crescent phases, and then when it was in its full phase, as it went back and forth near the sun, he would see it get smaller. And he actually correctly reasoned that, in fact, Venus is like the moon is orbiting the Earth, the Venus is orbiting the sun. And as it gets in its full phase, it's kind of farther away at the backside of the sun and reflecting that light back to us. As it gets closer to us, you see less of it because most of its dark side is now facing us, and the bright side is towards the sun. So it makes sense that it looks a little bigger in his telescope when it's closer. So that was really cool. And then the other thing he saw were these 4 little dots beside Jupiter. So Jupiter was a nice circle, and there was 4 dots that seemed to be orbiting around Jupiter. And so he discovered the moons of Jupiter called the Galilean moons. So those were pretty impressive things. And then around the same time, there was a mathematician named Johannes Kepler who was just looking at the positions of the planets against those constellations and trying to make a 3D model of where the planets were actually going, assuming that the Earth was traveling around the sun. And Kepler was able to write down very precise mathematical equations to describe the orbits of all the planets. He included Earth as one of the planets around the sun. And he discovered that they're ellipses. So let me talk about what that is. Should we try it? Yeah, there's this. Just ox plate. You have a Sharpie and 2 tacks. And so this is what you do. You just take the string and kind of pull it with your Sharpie to make a triangle, and then try to trace around. Whoop, there's the knot. Until you get back to your starting point. That's called an ellipse. It's a specific shape in which the distance, so this is a focus where the tack was. This is another focus. And this is what's called an ellipse. And the idea being that the sum of distances from one focus to any point and to the other focus to that point, the sum, L1 plus L2, for any point is a constant. Because that's sort of how the string went, right? So, what Kepler discovered is that you put the sun at one of these foci, and the planetary orbits are ellipses with the sun at one focus and nothing out there at the other focus. So, for example, the Earth gets a little closer to the sun. It turns out the Earth is closest to the sun around like January 3rd, which is weird. And then right around July 3rd, it's furthest from the sun. But it's not much. So there's different eccentricities. If you were to, let's do another one. If you were to put the tacks really close together, should we do that? Then you get a kind of an ellipse that looks almost circular. And this is much more to scale of what most planetary orbits look like, is something like this. Whoop. And that's the case of the Earth. You may have noticed that the sun, the Earth, there's the sun. It's only a little bit closer in January than it is farther in July. It's like about a 10% difference. And what's much more important for the seasons is that the rotation axis of the Earth as it rotates, as it goes around the sun, is fixed, so that the northern hemisphere is tilted more towards the sun in June than it is in December, when the northern hemisphere is tilted away. So that's what causes the seasons. So a circle is a special case of an ellipse. It's when the 2 tacks are touching, then you would get a circle, like 2 right on top of each other. Then it would kind of look like that. Okay. So if you ever heard about Kepler's laws, which are in your book, eccentricity is just a dimensionless number which tells you how squishy the ellipse is. So eccentricity 0 is by definition a circle. And then it goes up to 1 for, I guess, would be a very straight line. But comets happen to have very high eccentricity, so they only get close to the sun once per orbit, and then they spend most of their time way, way far away. So here's Kepler's laws of planetary motion. And these, by the way, they're not really based on anything. This is before Isaac Newton wrote down Newton's laws. Kepler just described mathematically what he was seeing with the positions of the planets. So first of all, planets and other objects like asteroids and comets move in orbits whose shapes are ellipses with the sun at one focus. And most planets there it goes, have low eccentricity, almost circular. Second one is this, sort of weird mathematical property which has to do with the speed of the planet as it goes around. Turns out that a line drawn between the sun and the planet sweeps out equal areas in equal times. So if area of A equals area of B, then dA, this distance, equals this distance, or then D, I guess A, is going to be greater than dB. And what that means is that the velocity at A is going to be greater than the velocity at B. So they go faster when they're closer to the sun. And then the third law is that something to do with the planet's orbital period. The square of a planet's orbital period is proportional to the cube of its distance from the sun. It's semi-major axis of that ellipse. So basically, the planets that are further from the sun have longer years. Okay. So we're almost done here, almost on weekend time, but Kepler's laws are empirical, kind of like the equation for kinetic friction. Remember that Fk equals mu sub k times n? There was no real justification for that law of friction. I just sort of said it, and it was an experimental result. So that's what I mean by empirical, is that it doesn't come from something more deep. We just write down the equation because it seems to look all right. A lot of scientists at the time, including Edmund Halley, the discoverer of Halley's Comet, believed that there must be some kind of force coming from the sun pulling the planets toward it. And they also believed that that force was decreased as the square of the distance from the sun, but they weren't quite sure. And it took Isaac Newton to invent calculus, which turns out you have to do in order to solve this, to write down Newton's laws, and then this fourth law, which is the law of gravity, the GMM over R squared law, which is this one. Do you remember it? F G of 1 on 2 is equal to G M1 M2 divided by R squared. That's the important fourth law, I guess. And how does this all relate to what we've been doing? Well, when you do projectile motion with this x and y, and you've got this a sub y is negative 9.8, and a sub x is 0, that kind of thing, this path is called a parabola. If you look at y versus x, it's a parabolic path. And an ellipse, if you really zoom in on one portion of an ellipse, you get what is very close to a parabola. And so this parabola is an approximation to the real thing, which is that this object is actually orbiting the center of the Earth. So there's an ellipse where one focus is the center of the Earth, the other focus doesn't matter. You're just up at the top, and that parabolic trajectory is an approximation in which we can neglect the curvature of the Earth and this change in the direction of gravity. I think that's all I really want to say about orbits, I guess. Next class, so have a great weekend. On Monday, I want to start talking about conservation of momentum and this idea that a big locomotive train carries a lot of momentum with it, which is why it's difficult to accelerate it.